All right, so continuing with chapter 10, we talked quite a bit about Venus, but we hadn't said much about its atmosphere. This slide to start the topic of Venus and its atmosphere, and the evolution of the atmosphere of Venus shows the primary atmosphere, which is important to remember, is shared between all three of the terrestrial planets that are, a little bit further from the sun. Those are Venus, Earth, and Mars. They all started with the same primary atmosphere. And actually, we can extend that. We can actually say all the planets started with that same primary atmosphere because it was just the primary atmosphere of the disk that formed the solar system. So yes, so I was being too conservative. It's everything in the solar system. But then we had a secondary atmosphere for Venus that was distinct, but not significantly different from Earth or Mars. But the current atmosphere of Venus is absolutely different from Earth. It is 96.5% carbon dioxide, as opposed to Earth's, right, which is about 60% nitrogen and 30% oxygen. Okay. And then just trace amounts of everything else. So here you could say that it's almost all carbon dioxide with trace amounts of everything else. Okay. So why is that? So what happened was the greenhouse effect. Recall we talked about the greenhouse effect in terms of its energy balance and the understanding of the energy balance via the concept of the greenhouse effect being one of the mechanisms, the variables that maintain that balance. That hopefully that both explained the greenhouse effect a bit, but also, talked about, the concept of energy and what planets are doing when they get out of whack, because really they're just getting out of whack. To use a very technical term, they're always tending towards equilibrium. That's really actually not what we're talking about here. Just reminding you, this is really the sort of pictorial representation of why these greenhouse gases are so good at doing what they're doing, which we didn't really see when we talked about the energy. There was a link to a video and some obviously follow up that you can do in the book, but the slides themselves did not get into it. So what is the greenhouse effect? Well, it involves a amount of energy getting trapped, right? Like a greenhouse traps light. By the way, the reason it's called the greenhouse effect is because of what greenhouses do. So, certain transparent plastics, but certainly glass has a ability to let through visible light. So we would say it's transparent to visible light. Glass is also transparent to quite a bit of ultraviolet light, at least typical glass is. But interestingly, glass is opaque, the opposite of transparent, to infrared. So glass has this interesting ability to let in visible light, but then if you have things inside of a glass house, well, like a greenhouse, right? Well, then they're going to heat up and they're going to glow in the infrared, right? And because that's the way that they maintain equilibrium with their surroundings. So they're releasing that infrared radiation, that heat. Well, it can't pass through the glass as infrared. So it's going to hit the glass and just bounce right off. There's other ways, obviously, for the energy to get out of a greenhouse. It can conduct through the walls and so on, and tiny cracks can lead to convection. But it still is that same principle of radiation getting reflected, having some sort of barrier that lets in one type of the electromagnetic radiation, but not the other. That also means that greenhouses don't let in infrared, but that's not going to be the primary way that things get heated up on the inside, right? I mean, so what? There's a little bit of, you know, heat light that isn't getting into the greenhouse. It's still the greenhouse is still going to be warmer than its surroundings because of that ability to trap the infrared that gets produced inside. Okay, so a little bit of background on the name. So that's what the atmosphere is doing, is it's acting like glass. So we've got here a concept of CO2, right? We know that CO2 can get trapped in oceans. We talked about that with Earth. Okay, so once you have a large concentration of CO2 in the atmosphere, okay, then you're going to have infrared light that's emitted from the surface, just like the things inside the greenhouse, and then getting reflected because of the atmospheric CO2 concentration and getting reabsorbed by the surface just to get, emitted and reflected again, right? So you have a amount of light energy that's trapped because of CO2 in the atmosphere. Without large amounts of CO2, this infrared light escaping into space becomes larger. There is some, it's not just one, bandwidth, and it's also not perfect, right? The it's not like the gas has 100% coverage. It's just a probability of it getting reflected, right? So, depending on how much CO2 you have, the proportionality between if you would, just size these arrows, right? Big thick arrow for lots of light reflected, small arrow for only a little bit escaping to space, for example, could represent um, how much, right, is doing each of those things, reflected or transmitted. Now, does Venus have oceans? No, right? So it doesn't have a way for the CO2 to get absorbed. So all of it is going to go into the atmosphere. So in that case, you have this extreme greenhouse effect. You have an atmosphere where there is all of the CO2 in the clouds and located in those cloud layers, none of it really being able to get locked into rock or stay in the ocean because the ocean is necessary to even lead to the lock into rock mechanism or final in state of the CO2. There's very few chemical pathways for the CO2 to get into the rock directly. Um, I don't know if there's certain types of lava that could facilitate that. Obviously, liquid states are going to be better at any sort of absorption than a solid, but water is crucial for effective CO2 trapping. Don't have liquid water on your surface, where's the CO2 going to go? It's just going to stay in the atmosphere. All right. So what happened is the water got disassociated. Okay. It didn't stay as H2O. What does that mean? Well, it split, right? So the hydrogen split from the oxygen. So this is dissociation. Okay. So you have an OH, right? And you've got an H, essentially a base and an acid, right? You have this splitting apart of these two molecules. Some Many of those can then escape into space. The hydrogen absolutely will. We know hydrogen is going to escape into space. All right, remember that. That's why that primary hydrogen didn't stick around. It's just too light to be held on to, except by the biggest planets. Right, foreshadowing things to come. But Earth can't hold on to hydrogen, neither can Venus. The OH, I believe, would also primarily escape into space, which makes sense because we don't, there's no significant, oxygen-based molecules still surviving in the, well, I guess, well, except for the carbon dioxide. So perhaps, further dissociation could leave a free oxygen that could combine with carbon. Um, but not 100% sure on that. A little shaky on the chemistry. It's not my area of expertise. The carbon dioxide simply survived. So the primordial carbon dioxide, yeah. So they're not. That's directly addressing my speculation that there wasn't carbon dioxide being created by any sort of like product of the water. Rather, this was this original population that came about as the secondary atmosphere. Remember, primarily from outgassing as the planet cooled, just like with Earth. But unlike Earth, where that carbon dioxide was able to get trapped thanks to our liquid oceans, there you go. It just stuck around. Okay. And since it stuck around and the water didn't, well, it makes up the whole atmosphere now, right? So now it's the only thing left and it's in significant amounts. So nitrogen, just like on Earth, survived, but instead of becoming 60% of the atmosphere, it actually went down to 3%, right? Because we, don't, we have an atmosphere that is, all carbon dioxide and a significant amount. All right. And they're saying that some of it might have gotten lost. Okay. And then they're comparing the masses and the different velocities. So if we look at the carbon dioxide, the average velocity, this is like the homework, by the way, this idea of comparing average thermal velocity to escape velocity. Actually, these are just all average thermal velocities, so there's no escape velocity comparison. But this is a concept that we skimmed over when in the slides on Mercury, which was chapter 9, because I pointed out that it would be explained in depth in the homework and hopefully made all the more clear because of like the way you get some practice with it, right? Some hands-on work, you know? So really that homework assignment called atmospheric retention serves the purpose of introducing these concepts, which do come up quite a bit in the slides. So if you do want to, refer to them, kind of see what's being said in the slides versus what you did in the homework, um, I think that could serve you well. But I'm not spending time on it in the lectures. But yeah, so looking at it, we have these much higher velocities for carbon dioxide and nitrogen on Venus. No surprise, it's so much hotter on Venus. Of course, that's a bit of circular reasoning at this point because, why is it so much hotter? Well, it's so much hotter because it's got the greenhouse effect, But the I just feel like I haven't, sort of completely justified that. It may be obvious to you. Sometimes I'm too concerned about thorough justifications of ideas, but suffice to say, Venus is a lot hotter. We talked about its crazy hot temperatures underneath its dense atmosphere. That's why these values are higher, right? Higher temperature, more energetic gas, it's bouncing around faster. So quite a bit faster for nitrogen than on Earth. Same for carbon dioxide. Okay, noble gases are they're quite a bit heavier. Argon, neon being the primary ones that exist. I keep saying xenon and neon. Neon, xenon's more rare. I was forgetting about argon, but there would be some xenon as well, just in much smaller amounts. Because it's a heavier element, thus more rare. But if you look at its masses, they're actually because they're atomic, even though they're further on the periodic table. The molecules aren't as big because they stay in an atomic state. So it's just that one atom by itself. That's the whole idea of noble gases. They don't make molecules. And so, they're actually end up being lighter, right? Even though they're heavier elements because they don't form these diatomic forms, or in the case of carbon dioxide, they don't form a full-on molecule. Okay, so point being though is that we had this is our evolution, right? That we have the carbon dioxide just sticking around, the water disassociating and going into space. All right. And that would have been what we call a feedback loop, if that idea is familiar to you, if it makes sense. Hopefully it does. What I mean by that is that you've got this carbon dioxide, you have nowhere for it to go because Venus is just a little bit closer to the sun, so it's a little bit hotter. The liquid water, it never is able to build up, right? Sunlight's more intense. So then no liquid water is building up. That means the carbon dioxide's sticking around, just, continuing to heat up the planet. Greenhouses are, warm up throughout the day, right? Well, here, that's the idea, right? You got this incredibly long day on Venus because of its really slow rotation rate, and so lots of time for each side of the planet to just take in all that sunlight, and so it just gets hotter and hotter and hotter. So now this water, which never was able to turn into a liquid and just stayed as a mist, it heats up so much that that's where the energy comes from to split it apart. So disassociation comes from the heating from a hot environment. The hot environment came from the fact that Venus couldn't do anything with that water. It couldn't quite liquefy it because it was too close to the sun. And so then, of course, as the water gets disassociated, it's not around anymore. And then you just have more and more of a greenhouse effect. Maybe you've heard the term runaway greenhouse effect. That's what I'm referring to. That's sort of feedback loop. One thing leads to another, and then it leads back to the original thing, and it just continues until you get to a final state. In this case, it doesn't go forever, but the final state of Venus is an incredibly hot planet. I mentioned that I'm not getting to the details of the landers on either planet. So that takes us to Mars, which was the primary goal. So here we are, Mars. Key characteristics. We've done this three times already. Did it for Earth, did it for Mercury. All right. Did it for Venus. Now Mars. We've done it to terrestrial planets. Okay. And let me check the time here. All right. Good. So I'll probably go for about 20 more minutes. All right. Just covering some important characteristics of Mars. In some ways, Mars is more interesting than Venus. Certainly, we've studied it a lot more. There's been all of these missions to Mars. People that are into space exploration probably know a lot about Mars. There's a movie about a person that gets stranded on Mars, The Martian, right? So Mars is a lot about it, but it doesn't have some of these explanations that I think require the same amount of detail that I was getting into with Venus or Mercury for that matter. So I think it. I can quickly summarize what I think is important about Mars. And of course that's the stuff that gets reflected in the questions, whether they're multiple choice or discussion or whatever. So Mars, small, right? It's only if you look at its radius, it's not that small, right? It's about half the size of Earth. But the whole trick is that size, when we're talking about radius or diameter, is one thing. Mass, which also could be a stand-in for size, right? You know, because mass is directly proportional to volume, right? As long as if you know the density, well then you know the mass is a lot smaller. So half the size, linear size, but a tenth approximately of the mass. Does that mean that it's a tenth of the volume? Well, no, because the relationship between radius and volume is a cubit. So if you cube one half, you just get one eighth. So this is smaller than we would expect from a straight cube relationship, because remember, volume is proportional to the cube of radius for a sphere, right? And it's proportional to the cube of any linear measurement for any 3D object. But here we got spheres. And the reason that this value is less than an eighth is because the density of Mars is relatively low for a terrestrial planet. Okay, it's much lower than Earth's or Mercury, which are the two highest, which you remember were in the 5 range, like 5.5. Okay, grams per cubic centimeter is the density of water. So we could say that Mars is almost 4 times denser than water, where Earth is 5.5 times denser than water. So Mars is just simply less dense as far as terrestrial planets go. It's got an orbital period of 687 days. All right. So its orbital period isn't quite 2 Earth years, but that's a good way to sort of remember it. It's a little bit less than 2 Earth years. Okay. So that's, that's the way that I've often heard it described as, quick way to memorize it. It's about 1.5 times further from the sun than Earth. So its semi-major axis is 1.52 AU. And remembering that an AU is 1.49 times 10 to the 8 kilometers, then we can do the math and find out exactly how many kilometers it is, and then convert that to meters, and divide by the speed of light to find out how many light minutes it takes for the sunlight to reach Mars. Not really, but you could, I guess, in a math question. But point being is 1.5 times further. That does make the sunlight significantly less intense. Here's a fascinating thing about Mars, both like kind of interesting and mundane at the same time, is it's got a day that's a lot like ours. So the day-night period is remarkably Earth-like. I mean, look at this, right? The rotation period, 1.026 days. Great. So, that is really what is going to seem like Earth, just as many hours of sunlight, just as many hours of darkness as you would expect on Earth. You wouldn't notice the difference, Okay. That also means that there's no strange relationship between, a solar day and a sidereal day, like with Mercury and Venus. Not at all, because, this is so small the rotation period is so small compared to the orbital period. You can obviously complete a day without significantly moving in the orbit, which is the same with Earth. The orbital tilt is also significant like Earth's, right? In fact, it's a little bit larger. All right. So similarities to Mercury and the moon do exist. All right. It's pretty barren and just, covered in craters, but not as much so. First of all, it's got a cool color that Mercury and the moon do not have. Okay. It does have some other features too, right? We had to sort of look for features that weren't just craters when we talked about the moon and Mercury. They were there, there was the scarps on Mercury, the big cliffs that are indicative of a shrinking of Mercury when it cooled. We have the Maria on the moon that only really are common on the near side of the moon, which are big lava plains, but mostly just craters. Okay. So we have highlands and mountain ranges on Mars. So actual geology. None of these false mountains like on the moon that are actually just piles of dust that settle after a crater impact. True actual mountains. Okay. We do have some big old craters left over. So the Hellas Basin is the largest crater on Mars. It's 7 kilometers deep. Pretty remarkable, right? For think about the crater walls on something like that. Okay. So no tectonic plates. All right. So there's no evidence of plates. We don't see the characteristic shapes of, where there was subduction and lines of volcanoes or anything like that. Um, I've heard discussion. I remember taking classes on planetary science and geology where, people would always put it out there. It's like that such and such publication or scientists have said, oh, there was some amount of tectonics if you define tectonics this way. Um, but it would be kind of at most maybe two plates. Basically, the plate tectonics that Earth has, are unique among the terrestrial planets. We don't see it on any of them. Mars would have been the best candidate potentially, but it even doesn't have plate tectonics. But again, there is some geology. Um, a famous feature on Mars is its giant canyon. All right, this is called the Valles Marineris. It is a long canyon formed by a magma upwell that teared the surface. So, and kind of how we talked about, the tearing that happened on the moon, right? All the weight of the lava moving the crust around. Well, that's what happened here. Tearing the surface on a planetary scale is kind of amazing to think about, right? Um, and I'm not sure where the upwelling is thought to have happened exactly, and what are the directionalities of the tear. But suffice to say that it was not caused by plate separation or anything like that, nor some sort of earthquake. Rather, volcanic activity leading to distortion of the crust. It's a huge canyon, though. Okay, they're comparing it to baking a cake, by the way. Right? See the tear in the cake. The size of this, Great Valley, Grand Canyon, but the Martian version of the Grand Canyon would stretch from one side of the continental United States to the other. So it puts the Grand Canyon to shame. It is a huge canyon, unbelievably, continental size canyon. The Tharsis Bulge is on the far side of so there's like this lopsided nature to it. So I think, yeah, it's on the far side of this one, of the Hellas Basin. And so, there's some ideas that it was sort of like an overall effect that, you had these big impact happen on one side, and that caused a bulge on the other side. So it's just a huge highland region made by upwelling magma. And the elevation of the Tharsis Bulge is really significant. In the same way that, like, the Hellas Basin was 7 kilometers deep, the Tharsis Bulge is many kilometers tall. And so if we compared it to like highlands or plateaus, it'd be like, Himalayan sized highlands, but stretching a much greater distance. And that sort of theme of these features being bigger on Mars, in the same way that everything's bigger in Texas, right? Well, everything's bigger on Mars compared to Earth. And that's because of the less gravity. So all these, like a similar geological event, like a volcanic eruption on Mars, can achieve much greater size because gravity is not working against it as much. Okay. So the smaller size of the planet almost, counterintuitively allows for some larger surface features. And case in point, perhaps you've heard about before, Olympus Mons, famous as elementary school trivia because it's the largest volcano in the solar system. Pretty cool, right? What is the biggest volcano? All right, go to Mars. It is huge. All right. It has a elevation of 22,500 meters. as compared to Everest, which is only 8,844. Of course, as you know, and can pedantically tell all of your friends and family, Everest isn't the tallest mountain on Earth. It's the Hawaiian Islands. Or if you really want to be cool, you pronounce whatever, however you say this. Ile de Hawaii. Not sure if I got it right, but it's 10,200, bigger than Everest. But of course, most of it's underwater. So we don't really think of it as a mountain, right? We think of it as an island. But if you counted from the bottom of the ocean, it beats Everest by a good 1,000 meters plus, maybe 1,500. Do the math. But then two times that size is Olympus Mons, so twice the size. It We couldn't get a mountain that big on Earth. The process of making mountains takes time. They erode, right? Why do they erode? They erode because of gravity. It causes landslides, causes instabilities. And so you can't create it fast enough to not have it collapse and fall apart, you know, before it's made. And it was possible to do it on that less gravity, the lighter, everything's lighter on Mars. Huge caldera at the top, which they have labeled. And the base is also incredible, 600 kilometers across. So what allowed it to be so tall? We talked about it's the low gravity. That's the defining part. These other statements, Mars shrank, is just wrong. Extremely hot magma. In fact, it wasn't any hotter. It was probably cooler magma. You can kind of see that because this is what's called a shield volcano. So it's just created by a steady flow rather than a big explosion. So there wasn't a big buildup of heat. The Hellas Basin impact pushed up Olympus Mons. No, it pushed up that whole region. The Tharsis Bulge. Okay, at least that's a hypothesis that I've heard from, which I think is pretty accepted, but I don't think it's the only hypothesis. So that's not it. All right, no wind or water erosion. I think that's can keep it around, right? Everything's sort of locked in place. But when I talked about the mountains collapsing, I said that they would sort of like fall apart. Maybe I sounded like I was implying erosion, but no, I said landslides, right? They break apart because of their own instability. That's gravity acting on them, right? They're always being pulled apart, and that's going to cause them to not not keep their shape, right? Right. So there we have, right? 2 times taller, gravity 2.6 times smaller. So they're making the argument, look, it's exactly the same proportionality. The How much taller Olympus Mons is compared to the tallest mountains on Earth? Well, that's exactly how much less the gravity is. Okay? you know, Not the most robust argument because you'd be like, well, these are just like samples, right? I mean, how do we know that this is exactly the mountains that could be made? But I think it's reasonable, and it's a wonderful way to introduce the actual gravitational value on Mars, 0.38. Okay. So the one here is not in base units. It's not the 9.81 meters per second squared, which is gravitational acceleration on the surface of Earth. That's how fast things speed up when you drop them. Rather, it's represented as one here, right? Just like the way we compare to the radius of Earth as one, or at 1 AU in the case of comparing orbits. And so if we wanted to find out what is the gravitational acceleration on Mars in meters per second squared, we would take this ratio of 0.38 and we multiply by 9.81, which we can estimate if we just round up 9.81 to 10, and then we got 3.8 just about. So 3.8 meters per second squared is gravitational acceleration. So, you'd be lighter. You'd feel lighter, about 2.5 times lighter, be able to jump further. What about the atmosphere? All right. Well, I said this before, but it's easily forgotten. And not the first thing that would come to mind is the atmosphere on Mars, pretty insignificant, but it's there. And we know it's there because, or one way that you might easily remember is like it's got wind. Maybe you've heard about the dust storms on Mars. If you haven't, that's fine. But, so if you got dust storms, you have to have some atmosphere. But here's the point I was going to make is it's mostly CO2, just like Venus. Okay, so Venus and Mars, almost entirely CO2 atmospheres. Okay, so it's mostly clouds of frozen CO2. All right, um, but some, let's just say some, which are pictured in this case, are made of water vapor and dust. There are water vapor clouds on Mars. Um, the fact that they have dust in them actually isn't a big surprise. Dust is necessary to make water vapor clouds on Earth. You don't think of clouds as being dusty, but if it wasn't for dust, you can't actually get the condensation in the atmosphere that leads to clouds. So there's always some dust in there. You basically need the particulates to start the whole process of the H2O like sticking together. Otherwise, the random motion overcomes the energy of the bond. But in this case, the dust, I would imagine have a greater dust proportion, so greater dust content than our clouds, the ones on Mars. And they'd had some other differences as well. Probably very low density, very disperse. They don't rain. So you never have a cloud on Mars that could get dense enough to hold enough water to actually precipitate. But there is some water moving around. There's very little water on the surface of Mars, but it pops up now and then. Frozen expanses of it that seasonally melt, and that would probably explain how there's some water vapor getting up into the atmosphere. Some cases where it seems to kind of come out of the surface, sort of bubble up, probably in a half frozen state, but very localized. So just little spots on the surface. Not that we've exhaustively explored the surface, so I'm sure we'll find out more. So water's around in frozen forms, maybe marginally in liquid forms, but more under the surface, but perhaps significant amount of liquid water under the surface. So you don't have to look far to find water, but you're not going to find lakes of it. Thin atmosphere, as I mentioned, the fast winds carry the dust around really effectively. Um, so the winds are incredibly fast. They're like 300 miles per hour, like would it be like supersonic wind on Earth? And that's made possible because of the lower density. If the atmosphere was denser, it couldn't facilitate such strong winds. So, having such a thin atmosphere means that when there are winds, they're really fast. Generally, they're not going to blow you over because there's less blowing, right? But things that just depend on speed would pick up that really great speed for whatever that would be worth. I can't think of an exact reason why the speed would matter, beyond at least not in combination with the density. There are cycles of dust storms. They're not exact, but they definitely do come in cycles. They can cover the entire planet, which is kind of fascinating. All right. And why don't we see small craters on Mars? All right. We've talked about missing craters on Venus. There wasn't really any missing craters on Mercury or on the moon, but we have a case of missing craters on Mars. We got a minute. Anybody want to put an answer out there? Where do they go? Why do the small craters disappear over time? Okay. Got a couple votes for three. Cool. Let's see. So three was a very reasonable guess, right? Covered up by volcanic activity. The only reason it doesn't quite hold up is because the volcanic activity stopped a long time ago, which I'm glad we're talking about it because I hadn't mentioned it. It definitely read the section in the book, is that when you look at that big old Olympus Mons, biggest volcano, you might think, hey, yeah, Mars is a pretty volcanic planet. Yeah, it was for a short time, billions of years ago. There hasn't been volcanic activity on Mars for I think 3 billion years. So it's around that time frame. So we got a 4.5 billion-year-old planet, and the water I know only existed for the first 600 million. So that only takes you up to 3.9 billion years ago for the disappearance of water. And volcanic activity didn't extend much beyond that. So, although I think that in a full discussion, this would be a fair point, in terms of the smallest craters, they've primarily gotten covered up by dust over time. They're just too small and they have been eroded. Yep, maybe covered, but certainly eroded. All right, there's the value of the carbon dioxide on Mars, pretty comparable to Venus, as I said. Okay. The primary and secondary atmospheres haven't changed, right? So we're using the same. So they are, yeah. So they actually are assuming the same ones. I wasn't sure with the secondary one if they had some variation based on different outgassing. These are all estimates. People study this stuff and have more refined numbers, right? But then the current atmospheres are where we see the difference. So Mars has an escape velocity of 5 kilometers per second. It's less, right? Because it's lower gravity. So it's significantly lower escape velocity than either Venus or Earth. And that means, all right, that we actually still can't have anything escaping into space. That's funny. Because I was thinking that maybe one of them did, but I remembered wrong. So yeah, so none of them quite can escape, but they get pretty close, right? If you look at nitrogen, 0.47, all right, in terms of its average velocity. Um, the noble gas is at 0.56. Yeah. So you might think, well, these aren't close at all. What are you doing? Are you moving the decimal place? Well, one kind of criteria is a factor of 10. That's what I use in the homework. That's the same as a online simulation, um, where I, you know, got that figure that shows the different planets and the different atmospheres that they have. So the idea is if a planet is expected to hold on to a particular molecule in its atmosphere for billions of years, it has to have a escape velocity for that molecule that is 10 times greater than the average thermal velocity, which is a huge difference. It means that the actual percentage, what if it was 9 times greater, right? Well, then there still would be this tiny percentage, like a thousandth of 1% of molecules that would ever, have a chance of being fast enough if the escape velocity is 9 times greater than the average thermal velocity. Because remember, the average is part of a bell curve. And so you'd be on the very tails of that bell curve if you're looking for a 9 times criteria. Well, if you have a tiny percentage that's not zero, even 10 isn't zero, but over billions of years, you might gradually lose it. And so the argument goes that, yeah, maybe 9 is good enough, but 7 or 8 really isn't, and we look at cases where that, it seems like that's where the gas has gone. It just really gradually escaped, but would have taken hundreds of millions or billions of years. And so with the noble gases, it's noteworthy that if you do multiply this by 10, you're greater than escape velocity. The nitrogen, you're not. So you're under it, but just barely. So escaping into space isn't going to be the major explanation, although we'll get closer. Despite its smaller size and lower threshold to escape, instead, it seems like what we had is kind of a freezing. So the water the water in Venus disassociated and then escaped. But in the case of Mars, it froze. So you have two different outcomes of where the water went. And that's kind of what you want to remember, right? What's the main takeaway here? Venus got so hot, the water split into lighter things that could easily escape into space. On Mars, Mars stayed so cold because it didn't build up an atmosphere. Well, you're probably wondering why. Well, I'll say in just a second. So then instead, the water was able just to freeze. Some of it would have gone underground as a liquid, and again, evidence supports that is some underground liquid water. Okay. All right. Curiosity is one of the rovers found formations similar to those on Earth formed by water. There's been lots of telltale signs of liquid water. Okay. But current theories highly suggest, based off of lots of measurements, based on rovers, modeling, that it would have been for about 600 million years from, the cooling point to the end of liquid water on the surface. So it's really just the very first epoch of Mars where there was liquid water on the surface, but it left it's mark, literally, right? Look at this. This is like an alluvial plain, where like a delta, right? Riverbeds. It's no joke. There's really like compelling evidence, almost like just there's nothing else that would explain these features other than significant amounts of liquid water. This is like an image showing like what the crater would have looked like full of water. And then the reason that they did this, that they doctored this image to fill up a crater with water, is because of this flow, this evidence of water flowing in, which would have been this point right here. It would match up. So the Jezero crater. All right. The polar caps have frozen water. They also have frozen nitrogen. So there's quite a bit of nitrogen ice on the caps. So it's not just ice. It's not just water ice. Okay. Here's ice in the soil, right? So it would have the rover track would have released it during the day. Would have been hot enough for the water that got pushed up out of the soil to be a liquid. So it probably was a sort of a liquid suspended between dust grains, and then it got pushed up to the surface just because this rover's rolling over dust that hadn't gotten disturbed recently, and during the heat of the Martian day, it would have remained as liquid, but then started freezing, and then sort of either quickly froze if it was cold enough. Direct sunlight could probably maybe keep it a liquid for a little bit, and but then freeze solid over the night, and then never really have enough energy to ever change back to a liquid because the low density atmosphere is just not going to let it phase change into a liquid. If anything, direct sunlight will sublimate some of it, but mostly, which means change it straight to a gas. But mostly will just stay as an ice and get recovered in the next dust storm. But the fact is, it's down there, right? There's just water sort of throughout the whole soil, at least in certain regions. I think they were actually down in a low point as well. Seasonal changes, right? So evidence of water seeping out of hillsides like this, all right, from the edge of channels. Liquid saltwater lakes found under the Martian South Pole. Not like they like literally, found them, drilled for them, but they've found them with satellite imagery. Carbon dioxide just totally survived. It's just in the atmosphere the whole time. Okay. And what's interesting is that, okay, so if the carbon dioxide totally survived, then why didn't it lead to a greenhouse effect that, kept the planet warm enough, right? Like how did the water freeze out? And essentially it like it just wasn't a thick enough atmosphere. And I believe it was just because it wasn't strong enough gravity to have a thick atmosphere. So the carbon dioxide's there, but it's not there in a big enough depth to really create a significant effect. So it's most of the atmosphere, but there was never that much to begin with because of the 1/10 the mass, remember, right? So it collected much less gas to begin with. So what happened to sulfur dioxide? All right. On Venus, it became sulfuric acid. On Mars, it absorbed into the clay through sulfuric acid. I'm just quickly going through this one, which is why there is no sulfur dioxide. Oh, and this shows the process. So this is acid rain on early Mars. So basically, when there would have been liquid water as well. Yeah. So the first 600 million years or so. So acid rain happens on Venus too, but it evaporates before reaching the ground. Interesting. Nitrogen stuck around. We've seen that every time, and just like with with Venus and Earth, the noble gas survived. Martian moons. I won't really hold you to accountable for these. I'd mentioned before that they're not large. So they're just look like asteroids. They're not differentiated. They're not spherical. See, neither of them is a differentiated body. Okay, so these are just rocks, big ones, but just rocks. Okay, their names are Phobos and Deimos. The size of the city, big rock, right? Comparing to Eugene, but don't worry if you're not familiar with Eugene. I'm not particularly. Just, it's an average sized city, right? Although I don't know the population. And 7 times more massive, which is further from Mars. Yeah, the mass does not relate to the distance, so it doesn't. Yeah, and then Deimos takes about 4 times as long to orbit Mars. So that there you can relate them. How would you do it? Kepler's third law still applies. And here you could just do a direct comparison because they both orbit the same body. So yeah. So here you would just use that direct relationship, t squared equals a cubed. Yep, Kepler's third law. Excellent. P squared, right? I said t because t for time, but we've been using p for period. Sorry for the confusion. Okay, so I'm going to go ahead and stop there. We've covered the things that I wanted to. Yeah, yeah. So I just saw Isabel's response to being like, "Oh yeah, not focusing." Yep. Sometimes these answers that aren't so cut and dried, right, aren't as satisfying, but that's the case, right? It's like, yeah, this okay, this is why this one thing matters a little bit more, and you sort of, you kind of build off of those ideas. Okay, stop the recording.